Alright, Chapter 4, Welding Stainless Steel. Stainless steel were originally developed because of their outstanding resistance to the corrosion. They also exhibit the good mechanical properties which can be important for the life of the structure of the corrosion and resistant. There are four types of stainless steel: the martensitic, ferritic, and the austenitic, and precipitation hardened. But these steel types, these steels exhibits a wide range of the mechanical properties, both room temperature and cryogenic temperatures below 150 degrees Celsius Fahrenheit. Stainless steel commonly used with the cover of the specification of the American Steel American Association of Testing Materials, or American Iron Steel Institute, the Society of American Automotive Engineers (SAE) and ASA, American Society of Mechanical Engineers, Army Petroleum Institute. Military and other federal agencies commonly use the stainless steel and other austenitic classes that meet the specification of the American Iron Steel Institute grades in the 200-300 series. The martensitic stainless steels and steels in the American Iron and Steel Institute 400 series are also used for the designing of the 400 series stainless steels. One of the most common extras cares because of the sensitivity, heating, of the training of the stainless steel used for the conform. The other specifications can be used whether the particular requirements must be met. Stainless steel welding electrodes are specified by the American Welding Society, and the military documents commonly used with the welding electrodes forming the fabrication meeting the specification of the American Welding Society: A5.4, A5.9, A5.11, A5.10, A5.22. Welding in stainless steel. Welding with stainless steel. The authentic chromium, nickel, steel are often used with the cryogenic vacuum system. The steels are all characterized with corrosion resistant, low magnetic, permeable, good high temperature strength, excellent low temperature ductility, notch toughness. Some of these austenitic steels, however, do have the characteristics that restrict their use in the cryogenic applications. Table 4.1. But the austenitic steels are considered the most weldable high alloy steels. The three basic factors that affect the weldability of stainless steel: the chemical composition base of the welding metal. 2. The microstructure of the base metal with the weld metal with the use of the current welding procedure and techniques. The chemical composition of the major constitute the stainless steel and iron, carbon, and magnesium. Silicon, chromium, and nickel. The chromium is primarily responsible for the stain and corrosion resistance of the steel. The affinity of the oxygen forms the thin, impervious protective oxide layer. The chromium also has an affinity with the carbon and forms the chromium carbonides, repeated rapidly between 800 to 1600 degrees Fahrenheit. When chromium carbonides are formed, they tie up much of the chromium and serve to reduce the corrosion resistance of the steel. Typically, this can happen in the zone next to or on either side of the welding joint. The phenomenon known as sensitization occurs because the region next to the weld is heated between 800 and 1600 degrees Fahrenheit. The welding arc of the welded joint is subjected to the corrosive environment. Knife line attack result. The three techniques used to mitigate the sensitization. These methods are going to be expensive and should be used only as sensitivity as a problem. Extra low carbon, less than 0.003% of the carbon steel grade with the steel can be used for the carbon content with the maximum amount. The soluble stainless steel and does not easily come out of the solution. B. The stabilizing elements such as colobium and tantalum can be used. The force of the carbonides preferably perforate over the chromium, thereby typing over the cover. Post-weld, the heat of the treatment can be used for the most common heat of the treatment technique is use the solution anneal with 1900 degrees Fahrenheit. The water quenched from this technique with all the carbon in solutions keeps it in there, rapidly cooling through the 1600 degrees to 800 degrees Fahrenheit range. 2. In fully austenitic stainless steel welds, such as the type of 310, the ductility soundness of the weld, depending on the carbon to silicone ratio, ideally with the ratio should be about 1 to 2. The increase of the silicone above the ratio causes the fissuring of the micro-cracking in welding material and welded metal with rapidly for the conductility. Increase in the carbon ratio causes the less severe decrease of the ductility with the affecting with the welding soundness. With the full austenitic stainless steel, the carbon steel silicone ratio must be closely controlled. This tends to limit the use of such steels where the welded joints with the best quality and ductility are required. Microstructural effects. The two microstructural factors affect the quality of the austenitic stainless steel. Welded joints ferrite with the contact with the welded metal with the base metal with the grain growing of the welded material. Heat affected zone. The following discussion describes the method of controlling these factors. Design can be used with the information specifying the proper purpose of the material and welding procedure materials. 1. Ferrite content. The fully austenitic welded joints often tend to develop microcracks fissures during the weld. To prevent this, designer should select the filler metal with the electrodes that will form austenitic weld deposits containing a small percentage of the ferrite. Such the welds are highly resistant to cracking. However, the ferrite content becomes too high with the hygrogenic application. The welded metal's impact strength of the surface of temperatures can be seriously reduced. For the application of the ferrite, the content with the weld metal should be within the range of 4 to 10%. The actual ferrite with the contact depends on the composition of the base metal, filler metal, and the electrode, or the electrode with the extent in which the welded metal with the deposit diluted with the welded parent metal. A Schaffer diagram in Figure 4.1 can help the designer establish both the percentage of the ferrite with the welded deposit with the filler metal with the composition necessary from form required ferrite with the welded metal. With the diagram is used to predict the amount of ferrite in the stainless steel with the welded metal on the base of the welded metal. With the composition diagram shows how the microstructure of the welded deposit is affected by the alloy elements stainless steel and that act like nickel or those and like chromium. The nickel equivalent group was the austenitic former included with the nickel carbon magnesium allows it is also made with the nitrogen content. The chromium equivalent is the group of the ferrite former includes the chromium molybdenum, silicon columbium, nickel equivalent is an ordinate with the diagram, and the chromium is to bisca. To estimate the microstructure of the weld of the metal with the design of the following formula to calculate the nickel and chromium's equivalence. Nickel equivalent is equal to the percent of the nickel times 30 times x to the percentage of the carbon plus the 0.5 tenths of an x of the magnesium. Chromium equivalent is equal to 70 chromiums plus the percentage of molybdenum at 1.5% of the silicon and 0.5% of the columbium. Nickel and chromium equivalents are calculated for both the bases of the welded material. The value of the obtained with the plotted with the Schelfheim diagram. The lines drawn between the 2 points indicated by the possible ferrite percentage that could be in the welded because of the base of the dilution. For the example, the type 302 with the stainless steel is welded with using the type 308 electrode with the nickel equivalent for the 302 the stainless steel is 12. The chromium equivalent is 18.25. When the point is plotted with the totally the austenitic region, so there is no ferrite. The type of 308 electrode will have the nickel equivalent of the 12, the chromium equivalent of 21, thus putting the close in the 10% ferrite line. The Schaffer diagram can predict only the amount of the ferrite microstructure, but also electrode composition that will prevent the excessive ferrite with the martensite content with the stainless steel welded metal. With an addition, the diagram is helpful to estimating the trending with the microstructure developed. The dissimilar steels are welded. If the piece of the carbon steel and stainless steel are to be welded together with the composition of the two can be marked for the diagram. The tie line drawn between them indicates the microstructure that may be encountered. Grain growth. Grain growth. The toughness and ductility of the heat-affected zone of the welding may be reduced somewhat because of the grain growth caused by the welding and heat. However, unless extremely highly welds are used, welding heats are used. Very heavy welded passes are deposited for the problem. Decrease the toughness, ductility result from the grain of the grain growth is not serious. If impacting test is the same with the welded joints indicates the notch toughness of the welded metal, but the heat-affected zone has suffered. The welding process should be modified to decrease the heat input to the joint and thus restrict the amount of grain growth. Or C. Pre-welded and post-welded heating treatments. Weld jointed with the stainless steel with neither the preheated nor post-heated. The techniques are make joints coolly and slowly because of the sensitivity with the resulting loss of notch toughness. However, the rapid cooling and after the welding prevents sensitization of the weld metal with the heat-affected zone. Multi-passing weld. Maximum interface temperature should be 300 degrees Fahrenheit. Stress relieving the austenitic steel and stainless steel and the welded joints should be avoided because of the seldom works in sensitization can occur easily. D. Welding crack. A welding crack, austenitic steel, stainless steels can be divided in 4 types: crater crack, star crack, hot cracks, and micro fissures or root cracks. All 4 types of cracking are believed to be manifestation of the same basic kind of cracking. At the hot cracking, namely hot cracking, easier as at an early stage micro fissures. Hot cracking presented with many difficulties some years ago, but now it can be prevented in weldments. Hot cracks occur in gradually and apparently with the segregation of low metal constitutes in the grain boundaries and reducing fissure and suspectability. The Figure 4.1 Schaffer diagram microstructure stainless steel weld. You have, let's rotate the picture. All right, you have your pre-printed Technical Manual 50885, Welding Design Procedure Inspection Department of the Army, 1968, copyrighted. Chromium equivalent percentage of the chromium plus the percentage of palladium 1.5x, silicon 1.5, carbium versus nickel equivalent of the percentage of nickel equivalent plus 30x of the carbon and 0.5x of the basic magnesium. And these are approximate borderlines, also in any range. Raw materials, non-ferrite, 5%, 10%, 20%, 40%, 80%, 100% ferrite. Martinians, austentide, approximately boundaries, austentide right ranges. Alright, hot cracks occur with the integrally with apparent with the segregation low metal and constitute with the grounding boundaries inducing fissures susceptibility. The formation of microfissures seems to depend on the 5 factors: microstructure of the welded metal, with the composition of welded metal, particularly with the level of residual elements. The amount of stress imposed with the weld is also cool for the high temperature range, with the ductility of the weld metals, with the high temperature for the presence of the notch of the insufficient cracks of the edge of the weld form many years of development. Microfissures overdevelop the deposit of the weld metal shortly after the solidification. However, the most recent work has clearly shown that microfissures can occur with the heated affected zones previously deposited with the sound welded beads. The microstructure of the welded metal with the strongly affected with the microfissure susceptibility. Welding metal having the wholly austenitic microstructure and a lot of the most sensitive condition promote microfissuring with the welding metal containing some of the delta and free ferrite and the inaustenitic matrix. The discussed above the chemical composition, both alloy content, residual element content, strongly influencing microfissuring. The susceptible the wholly austenitic stainless steel welding metals microfissuring is reduced by the small increase of the carbon content, substantial increase of the magnesium, also increase of the nitrogen content. The residual elements influencing cracking most often are used the boron, phosphorus, sulfur, or selenium, silicon, molybdenum, and tantalum. In welding, austenitic stainless steel, two different practices are now used depending on the microstructure to expect with the welded metal. Whenever the possible ferrite containing with the austenitic welded structure is used with the filler metal, with the be selected with the careful the welding procedure plain with the details secured with the small with the important with the amount of the delta ferrite with the Schaffer diagram. The discussed in the B above has been frequently determining whether the specified welded composition will be enough ferrite. B, while the wholly austenitic welded structure must be used with the welding materials contain lowest possible amount of the recognized crack promoter should be selected. In addition, with the amount of the alloy elements not to improve the crack resistance should be increased. Even with the best material with the most bearable welding procedures, wholly austenitic deposit are more crack sensitive with the ferrite with the containing. Therefore, all the phases of the welding inspection need greater care. 4. Base metal heated effect with its own cracking with welded austenitic steels, but there can be problems with a heavier section more than 1 inch of the thickness. Such that the cracking can have two causes. One of the intergranular form of the hot shortness of the heat affected zone during welded. The welded metal cracks because of the grain boundary liquefaction and embrittlement at near welding temperatures. Other causes of the cracking is complex phenomenon involved with the straight and induced imperception of the heating effect of the zone during the post-welded heat treatments. The surface at a high temperature above the 150 degrees temperature Fahrenheit. The change in mechanical properties result in the stress rupture failure under the certain circumstances of the form of the failure. Key of the problem is precipitation with the molybdenum carbides in the stress heated affected zone. As little of 0.1% with the molybdenum as residual element can be produced. The strain induced with the precipitation causing welding heavy suspension cracking during the service of the high temperature. Titanium stabilized stainless steel such as type 347 can be used. They help keep the non-stabilized stainless steel from the cracking. Other welded defects because of the cracking occurs with the weld metal incorrect welding process techniques used, but the defects are included with the prospect porosity, slag inclusion, incomplete fusion, inadequate joint preparation, undercutting. 1. Porosity of the cavity type of the discontinuity with the form of the gas entrap during the solidification of the gas with the form of the porosity of either the driven from the solution with the welded metal base, lower vulnerability at the lower temperature of the produced with the chemical reaction, molten welded pool of the gas is trapped with the welded metal because the solidification occurred because before the gas have the time to arrive at the surface of the pool. Porosity will form with less often very high current high currents or long arc lengths are avoided. The welding contact architectures must make sure that the variables are taken into account with the producer, developed, and the welder qualification test as conducted, especially true with the shielded metal arc welding process because of the high currents, long arc lengths, as well as large amounts of the deoxidation electrode covering, leaving little or combined with the electrode excess gas in the welding pool. Moreover, the type of the distribution porosity of the given with some indication of the cause. The type of the porosity is classified in acceptance and standard of the various codes. The American Society of Mechanical Engineers, American Petroleum Institute, or the American Welding Society is applicable. General, the type of the porosity depends on the distance between the individual pores of the group of the pores or group of pores. Uniformly scattered porosity can be found within in-many weldments, as with little concern because there is usually enough sound metal between the pores. Alright, cluster porosity is often associated with the transit air condition. In this instance are where the arc has been started with the south frequently contain cluster porosity. Linear porosity is usually found with the root of the pass, the construction and pass considered with a special case inadequate joint preparation. 2. Slag inclusions are oxide non-metallic solids that become the trapped and solidifying metal. They include either the capable, complete surrounded by the welded metal, or can be between the welded metal and the base plate with the shielded metal arc welding process. The chemical reactions between the welded metal and the coating materials produced for the non-metallic slag, the low weldable and welded metal, generally it will float to the surface. Sometimes the slag is forced into the welded metal, steering action of the arc of the float for the head with the arc and the cover of the welded metal. Proper cleaning and preparation of the welded joint, proper manipulation of the electrode will reduce the number of the slag. Inclusion of the welding contract can be used for the main precautions included with the welding procedures that developed and welder qualification testers are conducted. Incomplete fusion has occurred with the two welded beads with the base of the metal with the welded bead have not be fused together. The cause of the failure to rise with the adjoining of the material with the fusion temperature with the failure to dissolve any oxides or other foreign material on the surface of which with the new welded bead must be fused. Incomplete fusion would have prevented with the following and improved with the welding procedure, which should be include the cleaning of the preceding bead and continuous base metal welding joint, particularly where the care should be used with the welding stainless steel because of the high temperature increase amount of the chromium oxide formed with the stainless steel because of the hard and with the increased oxide layer. Inadequate joint preparation occurs with the fusion of the weld of the base metal with the root with the joint with the less specified with the design. Poor preparations affects with the wheel of the joints that will strengthen the surface of the root with the forms of the notch, and stress and concentration would lead to the early failure of the joint. Although poorly cleaned joint may cause the inadequate penetration, poor heat transfer condition in which the joint are more often fault, but the heat of the transfer can increase with the using wide angle the V groove with the large root opening. Undercutting refers to either the sharp receive with the side of the wall of the welded joint, reducing the thickness of the base plate with the toe of the last welded bead on the surface of the plate. In both cases, the welded technique is primary cause of the high currents on the high voltage as well as low currents on the fast travel. Speeds may increase with the tendency to undercut. If the undercutting is sharp and recessive with the joint side of the wall, it should be smoothed out with grinding and chipping because before the next weld is beaded in place. The American Welding Society specification and the American Standard Mechanical Engineering Boiler Pressure Vessel codes impose the limitation undercutting. 4.3 Joint design. Welding joints are prepared either with a plasma arc cutting with a machine grinding depending on the alloy. Before welding, the joint surface must be cleaned and all foreign materials such as the paint and dirt with the scales oxide with the cleaning may be done with the suitable solvents. The acetone, alcohol, liquor, and care must be taken to avoid nickeling of the gouging of the joint surface such as the flouncing and inferred with the welding operation. 4.4 Methods of welding stainless steel. The stainless steels are readily weldable and fieldable by shield metal arc welding, gas metal arc welding, flux core arc welding, submerged arc welding processes. Gas tungsten arc welding can be used in field fabrication, but it can be as a slow process. Shielded metal arc welding is most often because the equipment is portable and easy to use. Gas metal arc welding, flux core arc welding, and submerged arc welding are being used more often if in the field because of the economical produce of the higher quality welds. Manufacturer recommendation for this welding stainless steel should be followed. These include the recommendation joint design, preheat temperatures, and associated post-weld heat treatments and shielding gas. Alright, your shielded metal arc welding. The shielded metal arc welding has been preferred with the welding because of the versatility of the simplicity of the equipment and wide selection of the electrode available. All allow each of the important of the field welding and the application of the American Welding Society A5.4 specification stainless steel shielded metal arc welding electrodes. Electrode classification system. The shield metal arc welding electrode classification contains an E or 3 numbers followed by the dash, either the 15 or 16. The E designates the material and the electrode is an electrode. is an electrode. The three digits indicate the composition. Sometimes the letters following the three designation and these letters indicate the modification of the standard composition. The 15 and 16 specify the type of the current, but the electrodes may be used. Both designations indicate the electrode is usually usable in all positions: flat, horizontal, overhead, vertical. The 15 indicates the covering of the electrode is in lime time, which contains a large proportion of the calcium alkaline earth metals. So these electrodes are usually used with DC reverse polarity only. The designation indicates the electrodes that have a lime or a titanium type of the covering with a large portion of titanium bearings minerals. The covering of these electrodes also contain readily ionizing elements such as potassium, stabilized for the AC welding. The chemical reaction of the shield metal arc welding electrode requires the nickel, chromium, austenitic stainless steels are included with the American Welding Society A5.4 chemical requirements based on the as the deposit with welding metal chemistry. Chemical requirements do not change when 15 or 16 electrode is used. Welding metal mechanicals welded metal mechanical properties of the American Welding Society require the deposited welded metal to have the minimum tensile strength of 60,000 to 100,000 psi with a minimum elongation of 20 to 35% with the detailed requirements of American Welding Society 5.4. Recommended filler metals: austenitic stainless steel, welding handbook, section 4 with the metals and their weldability, chapter 54 with the 4% of chromium, molybdenum steels with the straight chromium stainless steel. Have a table given with the complete list of the base metal of the American ISIA number recommended with the filler metals to join the base metal. The table lists not only the chromium steels, but also have resisting stainless steel, all stainless steels, and the type of the stainless steel is not listed with the manufacturer's recommendation. Should be followed as an appendix for the American Welding Society A54 with the described intended for the use of the electrodes. Or gas metal arc welding 4.6. Gas metal arc welding is being used often in the shop of the field with the application between the office between much with less of the downtown electrode change with less of the loss of the resulting the stubs end for the splatter of the minimum the interpass cleaning compared with the shielded metal arc welding process. Gas metal arc welding can be done with the portion of the using either short circuiting transfer pulse voltage poor power supply. Gas metal arc welding has slightly less versatile with the shield metal arc welding because the welding gun is bulkier and the electrode holder is for the shield metal arc welding. Furthermore, the equipment is more complex for the expense, but the requirements some with more skill by the operator. Electrode classification system. The classification code of the gas metal arc welding wire consists of an E and an R. The three digits. The E indicates the electrode material. The R indicates the that it is a welding rod. C, the fillers are metals are used with the atomic hydrogen gas setting. Arc metal wire welding method used with the submerged arc welding and gas metal arc welding. Both letters are used. The three-digit number as such as 308 and is in ER 308 designates the chemical composition of the filler metal in a silicon. After the classification indicates Radar electrode contains between 0.5 to 1% silicon rather than standard 0.25 to 0.60% silicon, and L indicates this electrode carbon content not exceeding 0.3% specification electrode contained American Welding Society. Chemical requirements for the gas metal arc welding electrodes in the AWS A5.9 proportion of the elements similar with the electrical base metal with the same designation. All chemical analyses are based with as manufactured electrode wire. Welded metal mechanical properties. All welded metal tensile properties for the chromium, nickel, austenitic stainless steel electrodes are presented with the appendix of the American Welding Society A5.9. The mechanical properties are the same as those required for the shielded metal arc welding. Shielded gas. Two types of shielded gases are used for the gas metal arc welding. Pure argon and argon plus 2% oxygen minimum thickness, which can be used for the processing 1/8 of 3/16 of an inch. Alright, E, recommended for the filler metal for the chromium, nickel, stainless steel with the austenitic stainless steel. They're listed with the American Iron Steel Institute and specification number. The table, the covered electrodes recommended with the welds between the stainless steel and heat-resistant steels in the welding handbook, section 4, chapter 64. The stainless steel other than listed on are used for the manufacturing recommendation for the welded metal metals preheated. The temperature should follow the appendix of the American Welding Society A5.9 describe the intended use for the electrode type. Art 47, flux cord arc welding. Flux cord arc welding equipment similar with the gas metal arc welding offers with the advantage of the high disposition floor, fluxing ingredients to make sure the process is used with the primary and the flat of the horizontal position can be used with the other position proper electrode diameter welding currents that are selected with the flux core corrosion resistant chromium, nickel, steel electrode specified with the American Welding Society 5.22 electrode classification system. Flux core arc welding electrodes classified similar with the gas metal arc welding electrodes encoded in this code. The EXXXTY, the EXXX designation is the same as the gas metal arc welding electrodes and can be any of the material classification numbers previously noted. The letter T indicates the continuous tubular electrode while the powder flux within the tube. The suffix Y can be either the number 1, 2, 3 or the letter G. The number indicates the external shielding metal to be used during the welding, and an A1 or designates an electrode used in the carbon shield, and gas as in 2 designates the electrode used for the maximum argon plus 2% oxygen. 3 designates the electrode has no external shielding because of the is provided with the core of the material. The G indicates the electrode has electrode with an unspecified method of shielding. No requirements are to be used imposed on it. B. Chemical requirements. The table of the American Welding Society A5.22 presents the deposited welded material chemical analysis for the austenitic chromium, nickel, stainless steel, score arc welding electrodes. All classification of flux core arc welding electrodes have chemical requirements except for the G classification. Those requirements are always only agreed between the supplier and the purchaser. Welding metal mechanical property. The utensil requirement. The austenitic, the chemical nickel, stainless steel, the flux core arc welding electrodes are presented with the table of American Welding Society 522, with the tensile strength of the minimum vary from 60,000 to 80,000 psi with a minimal elongation between 20 and 35%. The G classification of the electrode does not have any of the requirements except for those supplied with the purchase and agreed upon. Shielding gas. The flux core arc welding electrodes can use the 3 types of shielding with carbon dioxide, argon, and plus 2% oxygen inner shield or inner shield. The inner shield method is used the gas-producing materials within the core of the electrode. The shield gas for the G designates the electrode with the non-specified recommended materials. Recommended filler metals with the austenitic chromium, nickel, stainless steel. With the recommended with the filler metal with the combination of the American Institute Steel. American Iron Steel Institute designates the stainless steel of the table of the welding handbook. See section 4, chapter 44. And the stainless steel, other than those listed on, or to be used with the manufacturer recommendation for the welded metal, should be filed with the appendix of the American Welding Society. The A5222, the flux core arc welding electrodes listed and intended to use for the electrodes. All right. Alright, the submerged arc welding process is limited with the flat position horizontal fill the webs because of the granulated flux used to protect the arc of the molten welded material. Metal submerged arc welding is specified with the American Welding Society A5 the same the specification of the gas metal arc welding. For the submerged arc welding, DC reverse polarity or AC alternating current may be used, but the AC flux is generally recommended with minimized silicone pickup of the oxidation chromium and other elements in general. Electrodes having the silicone content of 0.6% with less than the desirable submerged arc welding reasons. Fluxes usually result in some silicone pickup of the material classification, chemical reaction, mechanical property requirements are the same as those with the gas metal arc welding electrodes, as well as the weld condition. Recommendation filler metals, austenitic chromium, nickel, stainless steel is the same as those with the gas metal arc welding electrode. Are listed in the table of the Welding Handbook, section 4, chapter 64, with noted with the above discussion recommendation with the filler metals and other processed metals. 4.9 Special consideration welding stainless steel. Effective for the thermal property for the welding of stainless steel with the welding condition for the distortion of the thermal properties, coefficient of thermal conductivity with expansion melting point of stainless steel different. Some of those of the carbon steel with the different affecting the welding operation. Stainless steps must be taken to compensate with the effect of these thermal properties. The step is discussed in paragraph 7.5. The welding characteristics generally authentic. The stainless steel can be welded within 20% of the less of the heat within the carbon steel with the surface reason for the stainless steel have the higher electrical resistivity, and due to the carbon steel as a result, the stainless steel got the higher with the carbon steels. While the steel is the same, the real welding is used, but given the amount of the stainless steel can be melted with the less of the carbon with the same amount with the carbon steel. In addition, less heat of the current needed for the melt the austenitic stainless steel because of the higher the lower the melting points for the carbon. This finally with the less conductivity, heat conductivity wide the stainless steel is lower than the other steel, but therefore heat building up the metal from the welding operation flows away from the weld at a slower rate, with the result that during the welding higher temperatures reached with a shorter time. When welded austenitic stainless steel that warp the buckle more than the carbon steel. This is because the coefficient of thermal expansion for the austenitic stainless steel is about 1.5 times the largest of that of the carbon steel. The problem is further aggravated by the stainless steel's lower thermal conductivity, which tends to the contrary concentrate welding heat at the same in a small area. To keep the warping of the buckling at the minimum, the jigs of the fixtures are carefully set up with the welding sequence. The accurate fit up of the general have to be used. Reducing distortion should be avoided with the welding austenitic stainless steel, since it could lead to the sensitization portion of the welding joint. Alright, 3. Special precautions are required with attacking the welding using controlled distortion. Maintain the joint alignment. These precautions are not taken. The tack welds can be a source of welding metal, crack of the porosity, incomplete with the penetration, lack of the fusion. The tack weld must be made the same quality as the rest of the welding. It should be inspected to ensure that it is found sound and does not contain any tiny cracks, porosity. So for the tack weld should be grounded with smooth and concave contours so that it will be completely method with the final weld. Alright, 401, austenitic stainless steel is most commonly used for the cryogenic and European environmental equipment. 201, normally used for the cryogenic application, occasionally may be used for the fitting. 304, most often the cryogenic application maintain excellent notch toughness and low surface temperature, low carbon. 304L, less subject sensitive. 308 and 308L, containing the chromium and the nickel, through the type 304 and 304L with a better corrosion resistance, normally used for the other cryogenic applications of the base metal, most often the composition welding electrode filler metals wires. 310 Folios 310 ASI American Institute Stainless Steel American Iron Steel Institute. 310 Folios authentic subject to the cracking during the welding is sometimes used in fittings. 316 316L commonly used for the cryogenic application, causing molybdenum to improve the corrosion resistance, commonly used for fitting. 321 not used for the cryogenic applications due to long notch toughness. And 347 sometimes used for the cryogenic applications, stand for the chromium and to prevent the carbonide precipitation. Chapter 5, welding carbon steels and low alloy steels.